Today we are going to do section 6.3, which is the shell method of measuring volumes of revolution. What is a shell? Now, first I saved this thing for you. Okay, this is a shell. It's of course the inside of my toilet paper roll that ran out. Yeah, but imagine this thing. This is not perfectly round, but imagine that it is. That is the shell we're talking about. So the shell method is similar to the disk method in the sense that we calculate a bunch of shells in the function and then expand it from one end to the other until we cover the entire volume of revolution. Now, see an example of it. We will consider, for example, look at the next page where we have a function. Okay, your book has a interesting graph. What happens is that you will draw a line. Okay, to the left here is your function, the f of x. What you're gonna do is draw a line straight down. They made the line pretty thick, but ideally you just draw a line that's straight down and then spin that line clear around the y-axis. Okay, and then what does that make? That will make that cylindrical shell we're talking about. And then and what you're gonna do is calculate the volume of that one cylinder. Not this whole solid cylinder, just the shell. You know, the toilet paper roll. Only the thin layer around it. And once you've done that, then you sum up all the shells. Okay, imagine you make each shell from inside all the way to outside until you finish the entire volume of revolution. Of course, as you can see in this example, the f of x is being spun around the y-axis, and that's very important. Okay, if you get confused and and put in the wrong axis, then the whole thing will go to pot. Having said that, then what I just said is the actual calculation goes something, or proof goes something like this. What we have, of course, is that the shell has the volume of the shell, okay, which is base times height. Actually, to look at the volume of the shell, let's look at the next page or something where your book shows this thing. And then what you're imagining is that we have our toilet roll sitting there, right? What is the volume of the toilet roll? In other words, what happens when you unroll this thing and it becomes just a slab of flat object? Then its height is f of xi, and whereas x is the radius of the shell, and whereas then the diameter of the shell is of course 2 pi r, which is 2 pi xi, and then the thickness of the shell is delta x. So when you think about all that stuff, what happens is then the volume of your one shell, okay, volume of one shell is equal to, we have the 2 pi r, okay, that is the diameter of the thing, times, in this case, r is x to the xi, all right, and then times, that's the width, the entire width of the thing, times the length of it, and the length is f of xi. So that there's the length times width of your shell, and then the thickness of the shell is of course delta x. And then when we sum all this up into a Riemann sum, then we come up with a shell formula. The shell formula states that the volume of the shell of calculating the object revolution is given by you integrate from some proper endpoints, the limits. This is from the proper bottom number, top number. They're called well, whatever I think they're called upper limit, lower limit, or something. But anyway, so we have 2 pi radius, which is just x, okay, and then the height, which is f of x, and then then dx, which represents the delta x. And notice that you make absolutely sure that dx corresponds to delta x, and then the a and b is where dx increases. So in other words, when you calculate the volume of revolution, if you revolve around the y-axis, you will always be doing dx, and the other way around too. If you are revolving around the x-axis, then you have to do dy, because that's how the shell expands. So I have to pay careful attention to that. But anyway, this is revolving around the y-axis, okay, axis, and that's I'm currently on page 659, but you get the idea. Having said all that, let's consider, so that's the simple formula. The formula is fairly simple, but the actual integration might be very, very tough. And a lot of times the integration, if it's too hard, it just you have to use the definite integral to do the math. The definite integral calculator. Okay, just punch it in, and out comes some neat number. So let's look at example 6.12. Now in example 6.12, we have the function is as 1 over x, and then okay, and then we're going to spin it around the y-axis. Very important, from 1 to 3. So, and the exact situation, your book already draw a picture out there. So you can see that, and the picture only serves to make sure that we're spinning around the right axis. Okay, so then we're going to draw our shell, and here's the function, and then we're going from 1 to 3. We'll call this 1, this 3, and the function is 1 over x. All right, so imagine one of the shells. Okay, the shell is, remember, what does a shell look like? It looks like this, right? So we'll draw this thing, clear around one shell, okay, in a three-dimensional imagination. Okay, we're drawing only one. Okay, this isn't the whole thing. The whole thing doesn't look. This is just one shell. Now, the reason to draw it so that we can calculate the area and then the volume of the shell. Here is the radius of the shell, and that's x. Okay, and the height is 1 over x. So what is the volume? The volume of the shell, as following this formula, but we are also sort of reinventing it each time we do homework. The volume is the diameter, okay, 2 pi r, and r equals to x. That's the diameter, times the height, which is 1 over x, and that's the whole area of the shell, and times dx. Delta x, which is the thickness of the shell, which becomes dx. And then that should be the volume, right? Sorry, I see I messed up somewhere. What? Did I write the formula wrong? Give me a second here. Where's my formula? No, that's right. Yeah, it's right. See, you have three units. The radius, the height, and then the delta x. So 3 of them becomes unit cubed. So it all works out, right? There's no mistake. Okay, so we have this, and then we'll integrate this thing from, what was it, 1 to 3? 1 to 3. And that's about it. Yeah, and that turns out, in this case, it turns out to be a very simple integration, okay, because this cancel out. So then you only have 2 pi times 3 minus 1, which is, that's a 3. 3 minus 1, that equals, so the answer is just 4 pi. This is a very quick to integrate problem. All right, so that's that. And let's look at, so generally speaking, to use the shell method, you just make sure you did your calculation of your cylinder, okay, to calculate the area correctly. Make sure you know which one's the radius and which one's the height. And then, and then sum it all up in the proper direction, okay? If you sum it in the wrong direction, then your whole thing will be a goner. So remember this, which way is delta x? Delta x is this thickness, right? It's a very thin thickness here, right? The thickness of my toilet paper roll is delta x. So notice which way delta x is going is which way your dx should go, and then imagine this thing increasing this way. Okay, so you're calculating the x value. So generally speaking, if you spin around the y-axis, you better have dx in the shell method. All right. So that's how we do this problem, and the others are similar. Now let's look at the next example. What is that? That is that is the bundt cake. All right, we did the bundt cake in the previous section when we had to use the disk method, and the disk method is not that good for bundt cakes. It's far better to use the shell method for the bundt cake, and we can see that in a moment. Okay, now let's look at example 6.13, and almost identical kind of problem. What we do is we have a function, okay, and then spinning around the y-axis. And then we are gonna use shells to figure out what the volume is. So, example 6.13. We have f of x equal to 2x minus x squared. That's a upside down parabola. And then x is going from 0 to 2, and we're spinning around the y-axis. Okay, so all that is pretty clear. So I will draw the graph in your book, which shows in this function happens to go through 0 and then goes to 2. So and you're supposed to spin from 0 to 2. So, I mean, yeah, so the whole thing is very convenient. The fact that it's going to end up being a bundt cake is not really our concern. If you can visualize it or not, what's the diff? The point, because we just need to, you just need to be able to visualize one shell, okay? I lost my shell. What did I do with it? Okay, one shell. Remember this thing? Okay. Now, and then you visualize one shell. That's all you need to do. And then figure out where's the radius and what is the height. In this case, the radius is x, okay, and the height is f of x, which is whatever that is. I'll just write down f of x, and then that's about it. And then the dx is the thickness is this way, a very little. The delta x is right here, and it goes from 0 all the way to 2. And therefore, so this is all right. Let me get rid of this 0 so that it's not confusing. All right. Okay. So this distance here is x. Actually, this point is x. So then up to that point. And then so let's follow we can follow the formula, or we can just reinvent the wheel every time. So my shell right here, my toilet paper roll, has the surface area of pi r squared. What's r? R is just x. Sorry, 2 pi r. Why did I say that? I need the diameter, right? We need the diameter, which is 2 pi x times f of x, which is 2x minus x squared. And then we need the thing that is the entire volume, area of my shell, okay? And then the surface area, basically is the surface area on the outside. And then once we got the area down, that looks good. We'll multiply it by the dx, which represents the delta x, your little thickness, and that gives you the entire volume of the shell. And then we'll sum it up from 0 to 2 in this case, and that should give us the volume of the bundt cake. And if you remember what we did in the previous section, that bundt cake was hard to do. We ended up using the sine inverse or something, and we don't even know how to integrate sine inverse. And then I had to figure that out, so that was a real pain. Whereas this is a very similar function. But this integration, as you can see, is basically a piece of cake, right? Especially compared to what we had to do. So this one, and now let me double check what the book said to make sure I got it right. 2 pi x. Yeah, that's about it. Okay, and then you just do this integration and come up with whatever answer the book has. So pretty smooth. All right, and then Now, this is for when we spin around the y-axis. Well, what if we need to spin around, or if the object spins around the x-axis? Well, if it spins around the x-axis, then we just exchange, well, x-y axis, there's no difference, okay? You just exchange everything. That is, your formula changes variables. That is, instead of x, your formula is now in terms of y. But otherwise, x, y, what's the diff? There isn't any. Okay. The only thing you have to do is make sure that your function is given in terms of y. Okay. Such as in the example 6.14, which they give you the function g of y is 2 square root of y. And now, if the function is not giving to you in terms of y, then you need to plug x out of there, okay, if it's in terms of x, and do the inverse function until it is in terms of y. And then you apply the exact same trick that we have used, except with the only difference is with a different variable, and everything will come out exactly the same. And so please do example 6.14 as your homework. Next, let's look at example 6.15 on page 662, where you have a region of revolution, but you're spinning it around some other line than the x or y axis. Then what do you do then? Well, for the shell method, that changes nothing. That is, all you need to do is adjust the radius. Okay, you're spinning the only thing that's concerned that changes is the radius itself. Okay, the radius will be far longer or shorter, and then you follow the exact formula and come up with your right result right away. And so please do example 6.15 as your homework. Next, let's look at example 6.16 in the following page. What happens if your function is bound by two graphs? That is, instead of just one graph on top, there's something else on the bottom going whichever way. Well, in that case, all you do is you take the top function, subtract by the bottom function, because your cylinder is you need to cut out some of it. So once you calculate the subtraction, that is, your cylinder doesn't go all the way to the x-axis, it stops somewhere over here. So you take the first function, subtract the second function, and then that's the height of your cylinder, and then you continue doing the stuff. Therefore, please do example 6.16 as your homework. And finally, example 6.17. So far, we have learned several methods: the disk method and the shell method. Actually, we just found two. There's also something called the washer method, which is just a disk method with part of it cut out. And then, of course, the shell method, you also need to sometimes cut out part of it, right? The part that you don't need. And so the question is, which method should you use? Well, that depends on which one is the least painful, okay? And you're going to figure that out very quickly by staring at it. So please do example 6.17, where they want you to pick out which method is the best. Now, with that, we have come to the end of section 6.3. For homework, please do on page 668, do problems 125, 127, 135, 141. For problem 141, the answer key is wrong. So I will explain why that is. Continuing, 149, 151, 155, 162, and 163. For problem 163, ignore the condition that y equal to 0, because if you take that into consideration, your problem doesn't make any sense. But as long as you throw that out, then everything works out nicely. So I will clean the board, and so please go do your homework, and when you come back, I will talk about the homework. All right, now that you're done with your homework, let's talk about some of them. Problem 125, very straightforward, plugging in the numbers. Okay, you have a function y equal to x squared, and so on. It spins around the y-axis. So it's just, well, it ended up looking like a bundt cake, I guess, but we don't care what it looks like. We only care about what one shell looked like. Okay, so I draw a shell there, as you can see, and calculating the surface area of the shell, which is 2 pi x times That's the diameter times height, which is sine squared. And then integrate that whole thing, and the answer pops right out. That's that. And the same thing can be said of the following problem: y equal to square root of x. You take 2 pi x times the function square root of x, integrate it from the proper amount, right, from 0 to 1, and out pops your answer. Next, we'll look at problem 135, which is the same thing, except we are everything is in terms of y, and we're spinning around the x-axis. Okay, if we're using the shell method, always remember that to spin around x-axis, your shell has to be in terms of y for the whole thing to make sense. So then 135, other than the variable is now y instead of x, everything works out exactly the same. Your shell is equal to 2 pi times the radius, which is now y, and then times the function, which is the height of your, wait a second. Yeah, it's right. So your radius is now 2 pi is y, so it's 2 pi y times the x is now the height of your oops, my shell fell down. Well, anyway, so now the x, which is in terms of y, is now the height of the cylinder. When you multiply that out, integrate, and out pops the answer, and that answer is right. So problem 141 is y equals x cubed, x equal to 0, y equal to 8, and we're rotating around the y-axis. So let's draw that thing out and see what it looks like. First, y is x cubed. That for this part looks like that. And then x is 0. X equal to 0 is the y-axis. Okay, that's that part. And then y equal to 8 is this line, where y is 8. That's 8. So we have 3 lines bounding this stuff, and which means the area is in here. Okay, I'll put a few dots in here to indicate that area. Now, the reason I do that is because I want to draw another line down here, where this is 2, okay, because 2 to the third power is 8, where there's another area down here. And what I found is that your book, the answer given in your book, is spinning this area around instead of spinning this one. And I will demonstrate that. Now, to calculate spinning this one, we're going to use the shell method. Okay, here's our shell. We'll draw a sample shell right here. And the shell will go around like this, okay, because we're spinning around the y-axis, right? So for our shell, then we're spinning around the y-axis, which means that we're going to do dx, right? And therefore, we have, so everything goes pretty straightforward. We have we'll set this up as the distance will be x for the radius, so it's 2 pi radius, which is x, and then the y distance is, the y goes from 8 to x cubed, so 8 minus x cubed, okay, because it only goes down to here, so you have to figure out which way it goes, right? And then and so that's about it. Then dx, and that will be the volume of one shell. And then when we sum it all up from 0 to 8, then we get the whole thing. And that works out pretty well. And then that, if you do the math, will become something like 96 pi over 5. However, that is not what your book says. Your book claims that the answer is, this is the right answer, okay? Now, your book claims it to be 64 pi over 5. Now, what happens is, the reason, then I went ahead and calculated the area of this thing, okay? And then if you calculate the area of this thing around the y-axis, then it will be 64 pi over 5. And more importantly, see, take a look. I'll show you my notes. Yeah, this one. So the 96 pi is right, because if you calculate the other part right here, just the area down here, right? If you calculate that area, that is when it spins around, then the volume spun around by that part really is, this part right here really is the 64 pi over 5. And what's more, I can also show that if you were to add these two areas together, then it becomes the area of the entire cylinder. Not just part of it spinning, but imagine this whole thing is just one solid cylinder, and the two value does add up to be the whole cylinder. And that's how I am confident that your book spun around the wrong thing. Okay, if this is what they want, and that is the answer. And as you can see, this volume should be bigger than that, and eventually, and then the whole thing make up for the whole cylinder. So the answer should be this one instead of the one offered at the back. Next, let's look at problem 149, where we have some region that we are going to spin it around the y-axis. Now the region looks like, see my graph up here? No, my other hand. See this one? X is sine of pi y, and then y equal to x, which bounds some kind of an area there. Then once you get that figured out, then just use, this time, instead of using the shell method, please using the disk method will come up with a nice clean answer. As you can see that, remember the disk method is you will take the one on the outside, which in this case is sine pi y, okay, subtracted by the one on the inside, and and then in your calculation of the disk. And then once you've done that, the integral is not that easy to fix, I think, and because there's a sine squared in there, and I just used the definite integral calculator, and the answer popped out right away. Now, the disk method is by far the easiest thing to use. Before I used the disk method, I did the shell method because I wasn't thinking. I think I did it in the middle of the night or something, and then so when I tried to use the shell method, this is what happened. Okay, and I'm not going to show you too much of it because it didn't work anyway. I was stuck in a giant mess. So then that's when I thought, what am I doing? Why don't I use the shell method, which is far less painful, right? So that's what I did. Next, let's look at problem 151, which we go back to using the shell method. We're spinning something around the y-axis, which is straightforward. You have to calculate the height of your shell, which is the top function subtracted by the bottom function. And once you've done that, you multiply it by the diameter, and everything works out nicely. Except that the integration is not going to be easy, so we'll just use the definite integral calculator, and then the answer pops out right away. So that's that. Next problem, problem 155. The same thing. Let's see. You have right now you will use the shell method, where you have a top function which is something like 3x cubed minus 2 or something, and the bottom function is y equal to x. Doesn't matter. You just take the top function minus the bottom function. That's the height of your shell, and then the diameter of your shell is of course 2 pi x, and you multiply all together, integrate it. This is fairly easy to integrate, but I just plugged it into the calculator anyway, and out pops that answer that proves to be correct. And that answer looks like there's going to be a lot of work. So let's skip that and use the calculator. Next, let's look at problem 162, where we have to calculate the volume of a donut. The donut is given by spinning a circle around the axis. Okay, and in this case, our circle will be given as x squared plus y squared equal to 4, which I will draw here. Well, I'm only going to draw half of it, but that's the whole circle. You can use your imagination to see what the rest of it look like. And then there's a vertical line over here that we are going to spin it around. Okay, this is x equal to 4. And this is the circle has a radius of 2. That is something that's taught when you learn about circles and stuff. But in any case, the point is that we need to calculate the circle spinning around. And to do that, we are going to use the shell method. The shell shall be drawn like this. Okay, here's one shell, and here's my short but wide shell. Okay, and yeah, and you can imagine the rest of the shell, where this is the radius, of course, of the shell. Now to do this is spinning around x equal to 4, which is a vertical line, which is fine. But to do that, we need to find a function to represent what the vertical height is. So this is x, okay, and what is the height? Well, y in terms of x would be, if you plug this thing out, then we will have y equals to square root of 4 minus x squared. That is, if you plug this back in, this will come out. Okay, and that's another thing taught in circles, is that each one is in the square root form of a radius squared minus the other variable squared. In fact, this is also another way to recognize that something is a circle. It's either like that or like that. So y equals to 4 minus x squared, and that's this height. Okay, that's y. All right, and now we are ready to calculate the shell, kind of. All right, but first we should probably figure out where's the radius. Well, x is 4 here, and this is x, so the entire radius, the radius of this thing would be, of your shell, okay, of your sample shell, would be 4 minus x. Simply 4 minus x. And okay, so having said that, then we have the whole problem is ready to go, and we'll follow the formula to calculate the area of the shell. We have is 2 pi r. Okay, 2 pi r is how big it is around it, which is 2 pi x, and then the height of the shell is square root of 4 minus x squared. And together that should be the entire surface area of the shell. And then we multiply by the thickness of the shell is dx. So we are going to integrate dx, x going from 0 to 2. And as you spin wait a second, 0 to 2? No. It's from minus 2 to 2, sorry. Yeah, because the shell needs to go up here, and then that's only part of the donut. You gotta keep going all the way to over there, right? So then if we integrate from minus 2 to 2, then we should be okay. Minus 2 to 2. All right. So then and that's about it. 2 pi, right? Let me double check. Did I get what? Radius, I said radius is 4 minus x. See, it's important to double check, because sometimes I forget what I was talking about, right? This should be 4 minus x, because I said right here, right, radius is 4 minus x. So it's 2 pi 4 minus x times square root of x squared, and yeah, okay, so that's all good. That equal to let's see. Well, anyway, so then I plug this thing into the definite integral calculator, and out pops something. Oh, by the way, and I out pop my answer, which is 16 pi. Okay, and then so once I got 16 pi, I look at the back of the book, and I was wrong. It should be 32 pi. Why? Because I only calculated half the donut. See, the top half and the bottom half is the same, but to calculate it, I need to multiply it by 2. Okay, which I did write down in my notes. See, I mean, take a look. I did write down multiply by 2. See right here. But then when I was done, I forgot to do the multiplying. Okay, I just calculated the definite integral and call it done. And I never remembered to plug in the 2 there. So that's how I was able to get the wrong answer, even though I got everything right almost, except this part. So, but once you multiply by 2, then we're good. Okay, that's 32 pi. Now the donut, the mathematical name for a donut is called a torus, and it does have a standard formula to calculate it. And if you apply the standard formula, like I did, just for the fun of it, see, the standard formula is also gives you the 32 pi squared, which means the book and I are both right. Okay, so that's a that's a second way to double check that the book isn't wrong, that I'm not wrong, that we're not both wrong, right? Which is possible. So having said that, let's look at the last problem, problem 163. Problem 163 says you have a region where you have a function f y equal to f of x, and then another function y equal to f of x plus 1. So everything's lifted up, by one step. So you have two of them. And then this area is bounded by x equal to 0, y equal to 0, and x equal to a. And that sounds fine until you draw it out. See? Look at, I draw it out here. The problem is, as long as the function doesn't cross the x-axis like this one, for example, like this one, okay, it doesn't cross the x-axis, so then your region is clearly defined. But what happens if your function happens to cross the x-axis, and you have a condition that says y equal to 0 is part of the bound? Well, how does that work then? It doesn't really say. So my suggestion is that we forget y equal to 0 as one of the boundaries. Just this is good enough, okay? Just use x equal to 0 and x equal to a is sufficient to bound this thing. The bottom one is f of x, and the top line, the top function is f of x plus 1. And they go in the same direction. They just it's like moving the bottom function up a little bit. So then once you make that decision, then the integral is again 2 pi x, okay, times the height of that thing, and the height of your shell is just 1, because the top function is more than the bottom function by just 1. So the integration comes out very quickly as pi a squared, which turns out to be right too. It's also what the back of the answer says. So with that, that marks the end of this section.